the rate law and the actual rate of consumption of a reactant, they are kind of related. So the rate law is the relationship that you have between the rate of consumption of a reactant and the actual rate of the overall reaction, or how the concentration of a reactant is affecting the rate for the reaction. So when we're determining the rate law, we're looking at concentration of the reactants. You can find rate for reactants or products, but the rate law for any chemical equation is going to be determined by the concentration of your reactants, how much reactant you have. So I'm still using my generic equation here, 2 moles of A plus 1 mole of your reactant B, giving you 1 mole of your product AB2. So we can write down a generic rate law expression, and this works for any reaction. The rate is equal to the rate constant, the same rate constant that we saw in the Arrhenius equation, times the concentration of your reactants. That's what I have here. If you have 3 reactants, then you will have concentration of your 3 reactants, and they will be multiplied times each other times your rate constant. If you have 20 reactants, then you will have all concentrations for your reactants here, all of them multiplied by each other. There's no concentration of products here because the rate is this relationship between the rate of the reaction and the concentration of the reactants. Now, I have an exponent here, and I'm using just a letter, but those letters are going to be replaced by actual numbers. Those exponents are the order of, or that exponent is going to determine like how much of A you have, how much of B you have. So that's the order of, and those numbers are not equal to the coefficients. Concentration of A, you have a 2 for A, but that's not your coefficient. It might be, but that 2 is not coming from the reaction. So they are not equal to the coefficients. There are some exceptions to that, but that's something that we will go over in the final video for chemical kinetics. So M is the letter that I'm using for the order with respect to that specific reactant, which is A. Then N, letter N, is the one that I'm using to represent the order with respect to your other reactant B. If you have a third reactant, you need to include that one here, and you have to put another letter for the exponent for that third reactant. The order is a number, I already told you that, so we're going to replace those letters by numbers. But to determine the actual number that you have, we need to do some calculations. The calculations are very simple. You just need to remember a couple of things. Now, the overall order, those letters are representing the order with respect to a specific reactant, A or B. The overall order for the reaction is going to be given by the sum of all of the orders that you have. In this case, we have 2 reactants, so we have 1 order for each one. So the overall order for the reaction will be whatever number you have for M plus whatever number you can get for N. So the most common orders for a reaction are 0, first, and second order. You can actually get fractions, you can get something higher than 2, but the most common ones are this one, and these are the ones that you will see like in any general chemistry class. So a 0 order means that whatever rate you're getting for that specific reactant, that rate is not dependent at all on the concentration of your reactant. You can start your reaction with any concentration, and if it's a 0 order, the rate will be equal for any concentration that you can have for that specific reactant. And I'm going to show you with numbers. because usually it's easier for you to see what's happening if you look at numbers. I have here my reaction. I'm simplifying the previous one. So I have A going to be rate expression. It's always the same thing. You have your rate constant times the concentration of your reactant. In this case, I have one reactant. Now I'm telling you this is a zero order. So a zero order means that that exponent is going to be a zero. Now I'm giving you a value for K, and I'm using 1 just to simplify all of the calculations. So you can actually calculate the rate because those numbers, these numbers here, I'm giving you all of that information. Okay? The only thing that we're finding out is the rate. So I'm showing you like 3 different experiments. We have 3 different concentrations for your reactant A, and we're going to see how that concentration affects the rate when you have a zero order. So you can plug in your numbers here. Equation for your rate is the constant times the concentration raised to the power of a zero. So you have here rate for the first experiment. The concentration of A is 2, so I'm plugging in 2 there, and that's a 0. There's my marker here. And then we can do the same thing with the second one. The constant, it's for all of them, is 1. I'm giving you that number. Concentration for the second experiment for A is 3, and that's to the power of 0. And then for my third experiment, we can calculate the rate. That K is 1 times my concentration here is 4, and that's to the power of 0. If you actually check your calculator, if you have to, like, you will see that 2 to the 0 is 1, 3 to the 0 is 1, 4 to the 0 is 1. Whatever number you have and you raise to the power of 0, that will give you a 1. Okay? So if all of these ones are giving you 1 and your rate constant is 1, you're getting 1, 1, and 1. You're getting 1 here, but if the rate you're getting 1 because the rate constant is 1. I'm giving you that number, but if you have here 0.5, 0.5, 0.5, you will get 0.5, 0.5, 0.5 for all of them. That's not the point. The number is not the point. The trend is what you need to look at. Okay? You're getting exactly the same number for the rate for all 3 experiments, and the concentration for A is different. You're changing the concentration, but the rate is the same. That is happening because it's a zero order, and this rate here is not going to be determined by the concentration of your reactant. Okay? So that's the first one. And I have here like a representation. It's a simple graph representing like the numbers that I'm giving you, rate versus concentration. And I have my rate here, it's 1 for all of them. My concentration is 2, 3, and 4. So if you plug in your rate of 1 with your concentration 2, that will give you that point right there. Your rate of 1 with your concentration 3, that will give you this one. And then your rate 1 with a concentration of 4, that will give you the last one. So you see that you have a straight line. It's a flat line because the rate is independent on the concentration and it's not changing. You have the same rate for all of them. Different concentration but same rate, and that will always happen when you have a zero order. The second possible order is a first order. And for this one, what you have is that the rate, it's proportional to any changes in the concentration. So if you change your concentration by a factor of 2, the rate is going to change by a factor of 2. If you change your concentration by a factor of 100, the rate is going to change by a factor of 100. So they are directly related to each other whenever you have a first order. So I'm doing the same thing that we did with the zero order. I'm giving you a value for the rate constant using 1 to simplify everything. If you write down, and this is for the same A going to be. So if you write down the rate expression, you have your rate constant times the concentration of A. Since this is a first order, I have a 1 right there. And now I'm giving you numbers so we can actually calculate the rates. So I have concentration of your reactant A for 3 different experiments. Two, 3, and 4, the same numbers that I used for the previous one. So you can calculate the rate. Your K is 1, concentration is 3, that's 1. K is 1, your concentration for A is 4 to the 1. So you will see that 2 to the power of 1 is 2 times 1 for your rate constant. That's going to give you 2, and then you can do the same thing for your concentration equal to 3 and your concentration equal to 4, and you'll get. So your concentration is changing from 2 to 3, and the rate is changing from 2 to 3. Okay? So whatever is happening to your concentration, it's also reflected on the rate for that reactant. So I'm doing the same thing. I have a graph, rate versus concentration here, and I'm doing 1 through 4, 1 through 4. Your concentration equal to 2, the rate is equal to 2, so I have my first point there. When the concentration is 3, the rate is 3, I have the second one. And then the last one, concentration of A equals to 4, and the rate is 4. And you get a straight line, and the line it's going up because the concentration is increasing, and so does the rate. So that line right there represents a first order reaction. If you plug in your rate and your concentrations and you get a straight line, it means that the exponent that you're getting for that one, it's a 1. And the third possible order that you are going to get, it's a second order. Now for this one, the rate is proportional to any changes in concentration squared. If your concentration changes by a factor of 2, the rate is going to change by a factor of 2 squared. Okay? So same thing. If you have your reaction A going to B, the rate law expression will be your rate constant times the concentration of A, and this is a second order, so that will be a 2 right there. So I'm giving you numbers again so we can calculate what's happening to the rate when it's a second order. So you have concentration for A in one experiment here, 2, 3, 4. We can calculate rate for all of them. Okay, it's 1, then I have 3. My exponent is 2, so I'm using it 2. And then the last one, K is 1, concentration is 4. Let's do. So you're getting 4, 9, and 16. So that's what a second order is actually telling you. For example, if the concentration of your reactant is twice as much from experiment 1 to experiment 2, the rate from experiment 1 towards experiment 2 is going to be quadruple or 2 squared. Okay? And then you have a graph here. For a 0 order, you have a flat line. For a first order, you have a increasing and straight line, and then for a second order you're getting like a curve. Okay. So I did the same thing. I plug in numbers for rate, concentration, and I'm just writing down my numbers here. Concentration of 2 here with a 4 for the rate, concentration of 9, concentration of 3 here, sorry, with a rate of 9, and then concentration of 4 with a rate of 16, and you get like a curve. So if you're doing an experiment and you have concentration of your reactant and you're determining the rate experimentally, you can do the graph, and from the shape or how the graph looks, you can determine if the exponent is 0, 1, or 2. Okay. So if you do your experiments, you can change concentration, you can determine the rate, and you can prepare a graph, rate versus concentration. Depending on how the graph looks, you can find out the order. Okay. So I'm giving you the order, and with the order we find the shape of the graph, but you can actually go the other way around. If you're given the shape of the graph, you can actually find out the order for that exponent. Now there's a way that we can use to find out the order from experimental data. You can do an experiment, but in class you're going to be given the experimental data to find out the order. So I have here, and everything will look like very similar to this. You're going to be given a table, and in that table you're going to have concentrations in different experiments for your reactants and the rate for that specific experiment. So you have here an experiment, and you have concentration for your 2 reactants, and then you have the rate, concentration of your 2 reactants in experiment 2, and the rate, concentration of your reactants here in experiment 3, and the rate. So I'm using my equation here. I change it a little bit, and you can write down your rate expression is always the rate constant times the concentrations of your reactants. You have 2 of them, and those are increased to a power of something. What we're trying to get is how much is that number, M and N, the order with respect to A and the order with respect to B2. So this always works in the same way. Okay? So if you're trying to find out the order for reactant A, which is the letter M that I'm using here, if you want to find out the order for A, you need to look at your experiments. From your experiments, you're going to choose 2 of them where the concentration of A, the one that you're trying to get, is different, and the concentration of B, which is the other reactant, and you're not trying to get that order yet, it's the same. Yeah? And doing that, like what you're doing is like actually canceling out that concentration for your reactant B2, because it's going to be the same in 2 different experiments. Okay. So remember, always you're using 2 experiments where the concentration of the one that you're trying to find is different and the other one are the same. So looking at your experiments here, you want different concentrations for A, same concentrations for, this is B2, not B, for B2. So experiment 1 and 2 is not going to work out because you have the same for A and different for B2. Experiment 1 and 3 is not going to be working out because you have different for A, which is what you want, but you also have different for B2, which is not what you want. Okay? And then the final option is looking at experiment 2 and 3. Experiment 2 and 3, you have different concentration for A and the same concentration for B2, which is what we need. Okay? So using those numbers for experiments 2 and 3, I'm going to simplify the table. Okay? The same table, but I'm going to include only the experiments that I'm using, A, because these are the same, so I'm not going to look at them, and the rate. So it's the same table. I'm getting those numbers from the table that you're given. So we're using experiment 2 and 3 because in those two is where we have different concentration for A and the same concentration for B. So concentration for A in your experiment 2, it's 0.10. Concentration for A in your experiment 3, it's 0.25. You see? From the table. And then I'm copying the rate for those two. Experiment 2, and the rate for experiment 2 is 2.84, and the rate for experiment 3 is 7.10. So you're looking at your data, you're finding out two experiments where the concentration of A is different, the concentration of B is the same, because you're actually trying to get the order for A. That's why you need different concentrations for that one. So I'm simplifying my table, and now I'm going to do the following. You're going to look at your numbers. That's the first thing that you have to do. For you to have a zero order, you're going to have different concentration of A, but the same rate. And that's how we define a zero order. You have different concentration, but the rate is not changing because it's independent on the concentration. Here you have different concentration, but the rate is also different. So it means that it's not going to be a zero order. So now we're going to move to the actual calculation to determine if it's a first order or a second order. And the calculation is pretty simple. That's why I'm simplifying my table so I can show you with the table. You are going to divide 0.10 by 0.25. You are going to divide 2.84 by 7.10. Okay. So you're calculating that actual ratio. 0.1 divided, that's going to give you, I don't know what I did it, that's 0.4. And then you can do 2.84 divided by 7.10, and that's going to give you also 0.4. Now, whenever that number for your concentration, that ratio is the same as the number that you're getting for the ratio of your rate, it means that that's going to be a first order. If those two numbers are the same, it's a first order. If you get different number, then you have to move to the next one, which is going to be a second order. This number here, whenever you're getting the numbers equal number for both of them, it means that the concentration and the rate are changing by the same factor. I'm going to explain it to you really quickly. 0.10, for 0.10 to go all the way to 0.25, your concentration it's increasing by a factor of 2.5. If you do 2.5 times 0.10, that's going to give you 0.25. So your concentration between experiment 2 and 3, it's increasing by a factor of 2.5. You can also check this one here. For the rate to go from 2.84 to 7.10, it's increasing by a factor of 2.5. If you do 2.84 times 2.5, that will give you 7.10. So concentration and rate are increasing by exactly the same factor, which is your 2.5. And that is reflected on these two numbers here. Since you're getting the same numbers for those ratios, it means that the concentration and the rate are increasing by the same factor, and that's going to be a first order. So we already have the order with respect to A. Okay, A, and that's going to be A1. Now we're missing B2, which we're using the letter N. So we're halfway there. To find out the order for B2, we're doing exactly the same thing. You're going to look at the table and you're going to find out two experiments where the concentration of B2, now the one that you're trying to get, is different, and the concentration of A is the same. So I'm looking at my numbers here. I need different concentration for B2 that I can get between 1 and 2 or 1 and 3, but I need the same concentration for A. So the only possible option that I'm going to have is experiment 1 and 2. I have different concentration for B2, the one that I'm trying to calculate, and the same concentration for A. So I'm going to use my numbers to simplify my table again. Okay? So the numbers that I'm going to be writing down are coming from this table. Experiments 1 and 2. And now we're looking at the concentration of B2 and the rate. So concentration for B2 in experiment 1, it's 0.33 from the table. Concentration of B2 from the table for experiment 2, it's 0.66. The rate in experiment 1, it's 1.42. And remember, rate is mole over second. And then the rate for experiment 2, it's 2.84. That's a 1. So you have your simplified table, and the next step is to calculate that ratio right there. So 0.33 divided by 0.66, that's going to give you 0.50. And if you want, you can do this one too, but that's going to give you also 0.50. And what that means is that you have the same number, which means that the concentration and the rate are increasing by the same factor. And if you get the same number, that's going to be first order. So now you have the value of n, which is the order with respect to B2. And we can actually write down the rate law expression for the reaction. Your rate constant, reactant A, we found 1 for the order of A, reactant B2, and for that one we also have 1. Remember, you should do it in order. You're going to simplify your table and you're going to look at your concentrations and the rate. That's the first thing. If your concentrations are different but the rate is the same, that's going to be a 0 order and you don't have to do anything else. If that's not the case, if you have different concentration and different rate, then you need to find out the ratio for your concentrations and for the rate. And you're going to compare those two numbers. If the numbers are equal, then you're going to have a first order. Now, if those two numbers are not the same, the next step is for you to check if you have a second order. If those two numbers are not the same, what you're going to do is square this number. If you square the number that you're getting for the concentration and you get the same number that you have for the rate, it means that your exponent is going to be 2 because it's going to be a second order.